So welcome,
Yeah,
everybody.
I
Yeah.
can hear you and you can hear me. That's good.
Yeah, and everyone seems to hear as well. So yeah, this is a good thing. Yeah, so yeah, we won't. Don't worry, we won't go over the hour because obviously we are late. So not much, but we finally got to group actions. That's the final thing. We'll have the definition and a few observation, and then that's it. We'll carry on in the next in the next session. We'll build some stuff on top of the things that you will the basic definition stuff. Okay, so okay, so this is session 15 of 20. Let's see. We haven't. We should maybe in the next session or so we should make the transition. Not the next session, maybe the session after. We should probably make a transition to matrix groups already. So yeah. And then if that's the case, maybe, I don't know, 4 sessions will be okay enough on matrix groups, or we might maybe add an extra session. I don't know. We'll see. We'll see how it goes. But we are getting closer to matrix groups. Okay. Let's see. Another thing. So thank you, Bob. So Bob, this is the thing. It's a challenge. I decided to make it a challenge. So Bob, it seems Bob spotted a counter example. Yeah, his claim is that this thing doesn't hold for all the groups. So he constructed an example which is Z4 with mod 4 addition. So the challenge I want to give the others, I know Dimitri already said he agrees there is a typo. So now the next challenge is if everyone agrees there's a typo, how to fix it? Did I miss in the slides? Did I miss any critical piece of information, or are the elements not ordered proper, or there's something else missing in there? Yeah, but it's very interesting. He's saying that there are some groups that the thing is applied, but the thing doesn't hold for every. So he constructed an example. So the question is, look at Bob's construction from his homework, double check it, and see if there is anything missing. If you and Bob plus Dimitri agree it's a valid counter example, how to fix the statement then, the line 3 from slide 7. So that's a challenge. Okay. So just to recap again, from the past session, I think we went through left and right cosets, though we just stuck to left cosets mostly. We defined the notion of index of a subgroup, right? And then we covered normal subgroups. And finally, I think the last thing we covered, right, Georgia, was this notion of a quotient groups. So today we'll just, take it from where we left and see where we go with some results. And hopefully, if there are typos, that's actually a good thing. You'll be able to correct me. That's good thing. I have impression this at some point I will start to put in some deliberate stuff there. I mean, they will happen anyway, deliberate mistakes. So the first thing I want to go through today is this thing of a product of a subgroup or internal product, because there is also something called external product, direct product, as it's normally generalized. So suppose G is a group, okay? And suppose H and K are subgroups of G, okay? So they don't need to be normal, okay? So the internal product is essentially this set, so you multiply the group elements of each set, okay? So in this case, hk, little h times little k. That's it. Now, one observation here is that obviously it's already obvious from this proposition here, this theorem, is that this set doesn't necessarily form a subgroup of G. Okay. And here's the next proposition, this proposition that tells you in one of the conditions how it's, under what circumstances it forms a subgroup. So giving a G, so the proposition says, giving a group G, H and K, subgroups of G, then HK is a subgroup if and only if HK equals KH, okay? So here, obviously, KH is understood to be defined the same thing. So you just invert the orders, right? K and, instead of little h here, you swap the order, right? Obviously, if this is abelian, then it doesn't matter. But G doesn't, if G is abelian, it doesn't matter. But obviously, as you can see, when G is non-abelian, then the order matters. So yeah. And then the second part of the statement is that this is I hope it's a little bit clear here. What I mean is that if either of them, H or K, are normal, then the product HK is a subgroup of G. Okay, only one of them need to be normal, not both. If one of them are normal, then it automatically follows that their internal product is also a subgroup. Okay. You will see, I think there is a statement in the next slide or few slides. You will see an example where we'll integrate this part of this anyway. Okay, but for the time being, I give you this challenge. An example, I know, George, everyone is tired of permutation groups, but until we get to matrix groups, they are our favorite toy examples. So the example here is G to be S3, and then H is this made of identity permutation, and then this cycle 1, 2, and then K made of, obviously, because they are subgroups, they need to contain the identity. So K also has the identity permutation, and then but it has this cycle 1, 3. So the challenge is that you compute HK, okay, as of this definition, and then verify whether HK is a subgroup of G. And on top of that, it would be nice, I encourage you to compute the product KH and see whether that's also a subgroup, okay? It's possible that none of them are subgroups, so, but, it's just a challenge, a computational challenge for you, for you to see this thing in concrete action. Okay. Before I proceed, it's like a silence. Am I on? Is everyone? Because I think George disappeared. I cannot see him. Maybe because I'm highlighting the slides. All good. Okay. So everyone can hear me. Okay, cool. Thank you, Bob. Okay. So another notion I want, we need, because of some of the results, so a theorem in particular, is this notion of quotient map or projection map, canonical projection. So giving a group G and a normal subgroup of G, this map, we'll call it pi, it goes from G to the quotient groups of G by N is defined like this. Okay, so it essentially takes an element of the group G, and it takes it to the coset. Okay, and it happens for all G, obviously. So the question is, can you see that this canonical projection, as it's also known, is a homomorphism? Do you agree? This is a homomorphism. Remember, well, G is a group, but this, remember in the last session, we defined a group structure in here, right? So the claim is that this is a group homomorphism. Do you agree? Yeah, we are all on the same page. Or who disagrees? Is this a group homomorphism? Remember, this is a group and this is a group, and the map is defined like this. Okay, so Bob is not sure. Anyone else? I mean, you don't have to think it on the fly. Maybe in the study group, I claim this is a group homomorphism, and you should be able to prove this. It's a group homomorphism indeed. Okay, and if you find a typo, that's a good thing. And now the second challenge is given G, a normal subgroup of G and the canonical projection pi, the question is the kernel of pi the same as n equals n? Does the kernel coincides with n? If not, what is the kernel of pi? Okay, and a reminder in our context here, because obviously this is a very strange homomorphism, because it goes from G to this quotient group. So it would be all the elements in G that will generate the identity, the identity in the quotient group here, right? We defined this in the last session. So that's a challenge. Challenge number 2. What was the challenge number 1? Okay, yeah, it's that one. Yeah, so the order is okay. Okay. Do we have any questions, any doubts here? I know this is already becoming a little bit abstract for some of you because of the strange looking quotient group, right? But it's you just need to think it through. Take your time to go through it. Put it on pen and paper. You will be able to see this. And imagine if we add more structure to at the moment we are just considering algebraic structure. Imagine if we had topology. If we say, okay, this is a topological group, it becomes all a whole new level of abstraction, right? So, so this is really simple in the grand scheme of things. Okay. Let me just confirm again if I'm on. So I'm still on, right, George? Okay, I cannot hear any response. Let me check my network. Am I on, guys? Okay, you sound good. Okay. All okay. Yeah, so go through this. You will see why we need this map. This is a very important construction, because it brings us to this. I hope I didn't make any typo. It's also good if you correct me. So this brings to the isomorphism theorems. The first one, the first isomorphism theorem for groups. There is also isomorphism theorems for rings and so on. That's why I'm saying here for groups. So it says if a map F from group G1 to group G2 is a homomorphism, then this quotient group is isomorphic to the image of F. Okay. Remember the kernel. This guy here, care of F, is a normal subgroup of G1. There is a typo already here, so this should be G1. So I'll correct this slide. This should be G1. So I'll correct this slide. So I mean, it's implicit here that there's a typo here. So yeah, I'll correct the slide. So it says there is a natural, there is an isomorphism of this quotient group to the image of F. This is to say that there exists some isomorphism phi that goes from here to here. Okay. So another equivalent way of saying that is that, again, I'm sorry for this. There is a typo here for those watching. This should be G1. I mean, it's explicit here on the thing on the diagram. So this quotient, this map. So this theorem, this statement here, this statement that this is there is an isomorphism here, is the same as to say that there exists an isomorphism such that the following this diagram here commutes. You know, for those of you who like a diagrammatic picture representation of things. So you know, you have the G1 here. So you have the map F that goes to G2. In this case, obviously, it gets to the image of F, which is contained in G2. And then you have the canonical projection here, right? It goes from G1 to this quotient. There is another typo here. This should be F. Sorry for that. I knew there were a lot of typos, so don't worry. I will correct all these typos for those of you watching. There's a typo. Sorry for that. Yeah. So this is the first canonical. The first isomorphism theorem. So I have a challenge here, giving you concrete groups. In this case, the group of integers under ordinary addition, and the second group is the group Zn mod n addition. So the challenge is for you to go and construct a homomorphism, and then verify that this thing is satisfied. Make a construction. Yeah. Sorry for this. The thing, there is obviously there is a typo here. This is meant to be F, and in here this is meant to be G1. The same here. This is meant to be here G1. Okay. Okay. So that's the first isomorphism theorem. As the name hints, there are more. So the second one is this. Let's see. I hope I didn't make typos here as well. But yeah. Anyway, it says if G is a group and N is a normal subgroup. Remember, this symbol denotes N is a normal subgroup of G. I'm using N today, N from normal, just to make it a little bit more easier. And then let's H be a subgroup, an arbitrary subgroup of G. Then this statement says this: the product Hn is a subgroup of G. I think you already in the other there was a proposition that already hinting you this is true already, the previous proposition. In here we are stitching more things together. I should have left the other proposition until here, but I just decided to do it there. But yeah, it's the same. So if you prove the other one, this is like this line is already proven. But then the second line is that the intersection of N with H is a normal subgroup of G, and then you have this nice isomorphism here. Okay, this is, I mean, it's not that technically very hard to prove this if you digest well the notions involved that we covered last time and today also. So you should be able to have a go at this, even if it's hard. If not, look at some references on a thing on textbook or something. And the last resort, if you are struggling, just ping me, and I'll provide you with my own version of the proof. Okay. And there is also a third isomorphism theorem, which obviously, because I was in a rush, I didn't have time to put it, but I will correct the typos and then include the third isomorphism theorem in the slides, in the final slides, before uploading them to GitHub. Okay. And now we go to our friends, the group actions, long due. So I'm a little bit informal here, just to make it easy for people to digest. And I hope also I didn't make typos. So given a group G and a set X, a left action of G on the set X, let's say it's a rule, or it's a rule, right? A rule that mathematicians we invent that takes a pair in the Cartesian product. So in the Cartesian product of G with the X, so it takes a pair, this pair here, G X, so G belongs to the group and the X belongs to the set. And then it spits out an element that we write Gx that belongs to X. So in other words, an action is a map from the Cartesian product G times X to X, but not just any Cartesian product. Sorry, it's an operation that takes the Cartesian product, a map from the Cartesian product to X. But not just any map, it satisfies this. So if you take 1G, where 1G is obviously the identity of G, you apply the rule on X with 1G X, you should get X, okay? So 1G acting on the element X does nothing to X, so it leaves it invariant, okay? And then you have this very nice associative operation here, So these two, just notice the difference. These two operations, this is happening in G, okay? Whereas this one here, after happens, this is the action. The same here, this is an action, but then this is the thing here is a group. So sorry, the other way around. So you apply an action here, and then you apply the other action. Obviously, the action here will give you this action G2 on X will give you an element of X, and then you will act G1 on the result of the action G2 on X. Okay, so it should satisfy this, and very important for you to note this thing is giving any element of the group, we can define a map, let's call it a left translation, GL, that goes from X to itself as this. So GL of X equals the action of G on X for all in the thing, little x in the set X, okay? Now, another interesting thing that if you don't see this, it's not a problem. If at home you can, from now until the study sessions, with George, you can just go and think about it. This GL has an inverse map, which is this given like this. So the inverse map is this. You can act this inverse on the set, because obviously it's a group. So the inverse is also an element of the group. The action is defined on all elements of group, right? So this means GL is actually a bijection in X, and we know the bijections are actually permutations, right? They are elements of the symmetric group of X. So this is very, very interesting, because what this is telling us is we can define a map from the actual group to this by using the action, okay? And this is a homomorphism, okay? So the conclusion is essentially this: a left action of G on X will give us a homomorphism from G to the symmetric group of X, and likewise these homomorphisms will yield an action. Will yield actions on the thing on of G on X. Okay, so essentially this means that an action, a G action on X, is equivalent to a homomorphism. Is the same thing as saying group homomorphism from G to the symmetric group of X. Okay, so let's see some examples, abstract examples. Today I didn't have concrete examples because of lack of time, but you can have a look at this. Obviously, not trivially, I mean, like naturally, G can act on itself, right? Because G itself is a set. Even though we can dress it, we dress it on a group structure, we can also consider it as a set. And the natural group operation actually gives an action, right? So we take 2 pairs on the Cartesian product of G, and then the multiplication in G then becomes the action, and this is an action. The same here. Similarly, if we have G a group and H a subgroup of G, we can define a left H action, which will take the pair on the Cartesian product between H, the subgroup H and G, to this, where this operation here happens in G. So the multiplication between little x with the little h with the little x happens in G. This would yield. This will obviously be an element of G. Okay, and this one is a little bit more abstract, because again we are dealing with this very unusual group. Here I abbreviated this C here instead of writing in the coset notation. Instead of writing, I just abbreviated. But this is an element of obviously of this. So this, you can just write G prime n, for instance, and you will see that this action as defined here. This thing here as defined like this is an action of G on this quotient group. Okay, that's it. As I said, because of lack of time, I couldn't go and cover much. But for those of you, especially the newbies to this, just go through the definitions. Be very comfortable with this, and understand the stuff, the points made here. In particular, the equivalence between action and the thing, and the homomorphism from the group to the symmetric group of X. Okay, this is very important. Okay, with that, is there any questions? I told you we didn't take that much, apart from the typo, which I do apologize. I knew there were like a lot of typos. This other typo is a bit annoying because I like that theorem. The first isomorphism theorem is very nice. Okay, George, anything? Yeah. Am I still on? Who find it difficult, this notion of action? Is there anyone struggling with this? Let me go back. In the next session, we'll do more examples. Okay, so Stepan is saying it's a bit lost late Friday. Yeah, don't worry. I know it's a little bit late. Anytime we start late, even myself. That's why I was making mistakes with the thing with the slides, because it's been a long day. Yeah. Okay, so George can hear, but the microphone is dead. Okay, no problem. Yeah. So yeah, so we finally into anyone else apart from Stefano, who's having a little bit of a Friday. I mean, you go through again on this through these slides, and you do pen and paper and these things. You should be able to get this. Why is the stage empty? Okay. I think Crowdcast is still buggy. Okay, so the slides are back again. I hope you can see. Okay. No, I'm not highlighting myself. I want this. Yeah, I want to get us out of this thing of being at the thing on the top. How do I do this? Okay, yeah. So I'm back. Yeah. So maybe no. Okay, so can you still see the slides? Yeah, okay, let me put it bigger. Yeah, I don't know what's going on with the Crowdcast. Yeah, so yeah, anyone else have any questions or something? The important thing today is really this last notion, because you know, this is what we will be covering in the next coming session. In the next 2 sessions, we'll spend a lot on group actions. You will see a lot of examples before we make transition to matrix groups. So just look at it. You know, this is just an abstraction, and these things, you know, just take some concrete groups and you know, just create a rule. You know, you will see some of the rules that you are familiar with are actually behind scenes are actions. You know, so just look at that and you know, play around with it. You know, so. And by the way, there is also the notion of right action, but you know, if I leave that to you to define, it doesn't matter. We'll just stick with the left action. This is what what's most popular. Well, you can also go abstract and define left action and these things, but cover all the possible thing. But for us, let's just stick with the left actions. Sorry, I mean, you could also go around define right actions. Yeah. Yeah. So. Yeah, that's right. Permutations are group actions. Yeah, that's why this here. This is essentially what I want to say here. So I could have actually defined the notion of action as a, you know, directly as a homomorphism from you know, to say there exists an action, a left action, if there is a homomorphism from the group G to sim of X. Yeah, but I think that would have been a little bit more abstract than doing it this way, which is a traditional way of doing it. It's a little bit less abstract, but then you have the opportunity to you know, to show how the two things are equivalent. What's the difference between? Okay, I think it's a typo, Bob. Sim X and sim of it's a typo. I must have forgotten. 1M, so it should be sim X, is it not? The notation. Or have I added an extra M? It's normally sim X. Is it with 1 M or 2 M's? I'm not even sure. Okay, 1 M. Okay, so in that case, there's even more typos to cover. Yeah. Any other questions? I will correct the typo again. It's one with the 1 M instead of 2 M's. I don't know why I put 2 M's. Maybe because of my, instead of following convention, I will just following my my abbreviation thing. Sim, because the entire word symmetric has two M's, so I did. But it sounds right. Sim of X, I think. Okay. Okay. Well, George cannot come in to comment anything. Yeah, Bob. By the way, Bob, what do you need for your talk? I forgot again. So we have cassettes. You needed cassettes, right, for your talk? What else you need? Okay, orbits and the stabilizers. Yeah, in the next session we'll cover the I'm pretty sure at least one of them. We'll cover them. Yeah. Yeah, we'll cover them again in the more abstract. We cover them in the in the context of the examples that we've been going on the permutation, the symmetric group Sn. We'll go a little bit more abstract. So in a way, we reinvent them. We'll be reinventing them. So you will see that the abstract, so that will go to is actually given that you saw on the concrete, on the SN. We defined orbits in the context of SN. We'll define it in a much more abstract now that we have group actions. Okay, so, well, in that case, apart from correcting the typos, sim of x, there are two double n's here. There should be one. And this other typo here with the thing is meant to be G1. Yeah, I guess if you look at the diagram, at least I got it right on the diagram. It's implicit that there's a typo here. Okay, so, well, in that case, I don't want to take much of your time. Thank you, everyone, and yeah, we catch up in the next session. And by the way, think about fixing. If indeed there is obviously, it seems there is you are getting to a consensus. There is a typo in the previous in what Bob spotted. Come up with a fix. So that's a challenge. That's also an extra challenge. Okay, thank you, and have a good weekend, everyone. And yeah, we catch up next time. And sorry again for this for the typos and for the late start as well. Okay, I'll see you, everyone. George, thank you. I know your microphone is not working, but yeah, thank you so much. And yeah, we catch up next time.